Alright, this video is Unit 1, Lesson 4. It's going to be all about cube roots. And if you were in class for the square root lesson, this one will probably not feel too difficult. So I want to start with the function f of x equals x to the third power, or x cubed. We've been working with inverses this unit, and so my question is, what is the inverse of f of x equals x to the third power? Well, to answer that question, we're going to use the same procedure that we have used in all of our prior unit, which is we are going to, remember this is a y value, f of x just represents y, and we're going to switch that x and y in the equation. We do that, remember, because inverses and functions, or inverses that go with certain functions, end up switching those x and y values. So one way that we can algebraically find an inverse is to switch the x and y physically, and now we're just going to solve for y. Well, right now the only thing that is happening to y is that it's being raised to the third power, so we need to undo that. Well, if you have a second power that you need to undo, you square root it. If you have a third power you need to undo, you cube root it. And so what we have on this side of the equation is the cube root of x, and then the third power and the third root cancel each other out or undo each other, so we're just left with a y on the right hand side. And that is our inverse function. So if we write it in function notation, it would be that the inverse of f is the cube root of x. Now please note that the 3 is small and it's sort of tucked in snug to that root. You don't want it to look like this. That looks like 3 times the square root of x. So this is different than that. This is the cube root of x. So just be careful with how you're writing it and try to be precise. So that's the first function I wanted to look at. Here's another one. What if our function is f of x equals the quantity x minus 2 to the third power plus 5? Same thing, we want to find the inverse. So we'll remember that this is a y value, and we will switch our x and y. Everything else stays exactly the same. The y became an x, and the x became a y. And now to put this inverse into function notation, we need to solve for y, or get that y by itself. So we'll start by subtracting 5 from both sides of our equation. So you have x minus 5 now equal to the quantity of y minus 2 to the third power. Well, we've got this third power now on the right side of the equation, and we want to undo that. So we'll do our cube root of both sides of the equation. That root will we take in the root of both that x and the minus 5, the whole quantity x minus 5. So make sure you show that all of that is in the root. So the left-hand side is the cube root of x minus 5, and over here, the root and the power undo each other. They cancel each other out, and so we have just the y minus 2 left over there. And we're almost done. We're trying to solve the equation and get the y isolated, so we just need to add 2 to both sides. Now be careful here, that 2 is not going to sneak into that root. It's not going to combine with that 5. We literally have this quantity that we had before, the cube root of x minus 5, and we're adding 2 to that. That is going to be our y value. And this will be the inverse function then. So if the function f is x minus 2 to the third plus 5, then its inverse that goes with it is the cube root of x minus 5 plus 2. So that procedure is pretty similar to what we have been doing in the past. Alright, so now I'm wondering, I have this new type of function now, this cube root function. I'm wondering what what it looks like. So we're going to fill in this table of values and draw a graph to see what it looks like. So our function is the cube root of x. We're just going to start with that basic parent function. And we're going to substitute these values in, starting with -8. So the first thing that we're going to ask our calculator to evaluate, whoops, I missed the negative, is the cube root of -8. If you're using a TI-85 graphing calculator, the cube root button, how you find that is you hit the math button and it should be the fourth one down. If you're using a scientific calculator, sometimes you'll see that little cube root with the 3 next to the root. Sometimes you'll see a little x next to the root. If your calculator has the one that looks like this as one of its buttons, you would type the 3 and then you would hit that button and it should make it look like this on your screen. So it should be one of those two things. Again, in the graphing calculator, hit the math button, which is on the left hand side, and you should see the cube root as the fourth choice down. So cube root of -8 is -2. And we keep typing in those values and filling in the table. And we end up with something like this. And if we plot those points, we'll start to see what shape this function has. Ooh, that's a big. Okay, so those are our points. Sorry, they're a little bit big, some of them. And this part of it, you can kind of see is a similar shape to that square root shape. It doesn't grow quite as fast as a square root, but it's a similar shape. But a cube root also has this other side. It's radially symmetric. Anyway, it goes through the point here in the origin. So it's this shape. Let's see, there's a couple questions on here. Did you get any of the same error messages as we did when we were working with square roots? And we did not this time. The domain of this function, remember if we're writing it in interval notation, for example, we would think about from the farthest left to the right, or if you prefer, you can write it as all real numbers. The range is also infinite. Sometimes people will think that it's not because it does look maybe like it's getting fairly flat, but it does not flatten out. It grows very, very, very slowly, but it does continue to grow up higher and higher on this side and lower on this side. So don't be fooled by its slow rate of growth. It does have an infinite range. When we talked about square roots, we had some issues with our original function when we wanted to find the inverse, and we had to, we had to sort of ignore or limit the domain of our square root so that when we reflected it and thought about the inverse, we would have this square root function that's shown in blue. So we had occasionally domain restrictions and things like that showed up in our equations. My question is, are we going to have the same problem with x to the third? So I want to show you what that graph looks like. Looks like this. The pink one is showing x to the third power, and the blue one is showing the cube root of x. Let's see, I'll write that in there. This is x to the third. This is the third root of x. And if you remember that one of the ways we can test to see if an equation is a function is we can use the vertical line test. Let's get a vertical line here. And if we're testing the pink function, or the pink graph, to see if it's a function, you can see that it does in fact pass that vertical line test. That whole pink graphs. So the pink one is a function, and the blue one, the cube root, if we think about that vertical line test, it looks like it also passes. Sometimes right here people think for a minute, oh, it's not passing the test. If we could draw a perfect line that had no thickness, it would pass the vertical line test, but because we're using, I'm trying to make it so that you can see it on the board, I have to make my line kind of thick so it looks like it doesn't pass right there. But it does actually pass the vertical line test. The cube root of x is a function, and we won't have to worry about any domain restrictions or anything. Now I'm not going to use tables to graph these anymore. We're going to use a pattern to help us graph them so that we can be faster. And mathematics is kind of all about using patterns and structure to help you do things efficiently. So here's another picture of the cube root of x, and I kind of tried to show the pattern on here. As we're graphing cube roots, we're going to start with this, I'm going to call it like a central point. It's called an inflection point. And so that's where we'll start our graphs, and then we'll do the two sides, the two halves of it. We'll go up 1 over 1, up 1 over 7 to get this sort of top half, and then from that same inflection point, down 1, back 1, down 1, back 7 gives us this side. And that gives us the entire shape. So it's a 1-7 pattern. So let's try that. We're going to do a few graphs. So we're going to first look at each of the translations separately, and then we'll do a couple together. So this first graph is a vertical translation. Remember, you can tell by looking at a function if it's a vertical translation because it's a constant that's added to the function. In this case, we're going to add the number 3. So if we're thinking about where that inflection point is, in this case, it's going to be at the point 0, 3. The 0 comes because there's nothing added to the x inside the root, and then the 3 is the constant added after. So that's shifting the function up 3 units. So now that we have that inflection point marked, we can do our pattern. It would be up 1 over 1, and then up 1 over 7. Remember, that's a 1-7 pattern. And that gives me this part of the cube root, but I know that it also has the other side, so I need to go down 1, back 1, down 1, back 7, and that gives me the other half of the graph. So here is our cube root that is shifted up 3 units. Domain is all real numbers. Remember, you can think about that from left to right if you like. I don't care which way you write that. And then the range also is all real numbers. So that's a vertical translation of a cube root. Let's look at a horizontal translation. You can recognize a horizontal translation because the change that's made, the thing that's added or subtracted, is with the x under the root. That lets you know it's a change to the left or right. So in this case, our inflection point is going to be at -2, 0. So right here. From there, we'll do our pattern, up 1 over 1, up 1 over 7. You're going to love counting out those 7 to the side. And then the other half, down 1, back 1, down 1, back 7. And so here is our cube root. Domain and range, all real numbers. For cube roots, you will always see that in the same. All right, a vertical stretch. Let's see how this changes the graph. So our function is going to be y equals 2 times the cube root of x. So we're stretching it by a factor of 2. Our starting point, when we're graphing it, is going to be, in this case, the origin. From there, our pattern is going to change a little bit. It is still a 1-7 pattern, but it's stretched by 2, by a factor of 2. So that means we're going to go up in this case to, or now that we're doing the second half, down to that 1, down to that 7. So you can see it's that same shape, it's just stretched out much wider for the group. So if ever you find yourself in a situation that you have forgotten the pattern and you don't remember if it was 1, 5 or 1, 9, or if you've just forgotten what shape it is completely, you should always just use a table of values. So if you've forgotten, set up a table, pick some Y values, just kind of cover the whole space a little bit to see if you can use those X values to substitute into the equation, get the Y values, and then just plot those points, and hopefully it will help you find your shape, okay? So if you forget a pattern, using table of values should help you in any function type. Okay, we're just going to do 2 more graphs with multiple transformations. So our functions potentially could have all of these changes to them. It's going to have that starting inflection point at HK, so it's going to be up right here, up down here. And if you have an A value in front of the root that's multiplying that root, that's a stretch. So let's try a couple. Here's our first function. F of x equals the cube root of x minus 1, and then minus 2. So our inflection point, our starting point that we're going to graph first is 0.1, -2. Here it is, 1, -2. Check to see if there's a stretch. In this case, we don't have a stretch, so it's just a regular 1, 7 pattern. So from this point, up, 1 over 1, up, 1 over 7. And then the other side, down 1, back 1, down 1, back 7 over 7. And there's our cube root. Domain and range are all real numbers. You can write it this way if you like to a little bit more. Hey, one more, and we're going to change this function just a little bit. I want to show you what happens if that stretch is a negative number. So we're going to slip a little negative sign in so that it's -2 times the cube root of x plus 4 minus 1. So our starting point as we graph this is going to be at -4, -1. That would be right here. And we have a stretch of -2. Again, that's because I did add that negative because I want to show you how a negative stretch would work. So normally our pattern would be up 1 over 1, up 1 over 7. This stretch means that from that first point, we're going to go down 2 over 1, down 2 over 7, like this. So on the right-hand side, it's going to look like this, and then we'll go up and back, and the left-hand side will look like this. It's taken that shape that you normally have, which looks like this, and it's flipping it over so that it's more like this. And sometimes that can be tricky, so visualize as I do it, but it is actually reflecting it, it's flipping it over. So stretch -2, starting at this point here, we're going to go down 2 over 1, down 2 over 7. And then from that same inflection point, up 2, back 1, up 2, back 7. So something like this. Domain and range of this are, of course, for all cube roots, it's going to be all real numbers. So that's it. Today, I mean,